The next topic we have is Anova, which is the analysis of variance. Again, we're going to start with a little bit of a story because Anova is difficult to explain. This is the hardest statistic that we're going to do this semester, and it's also the most brilliant one in my estimation. So I want you guys to have a sense of what actually happened, and also the insight that you might be able to have in something that we haven't yet figured out. Because I think you'll be able to follow along the insight that was Serrano Fisher's that enabled us to understand how to do Anova and what a revolutionary technique it was. It's probably the most common statistic that we're going to learn. Maybe I think correlation is probably the most common one that you'll see regularly in terms of inferential statistics. Anova would win, but correlation is a descriptive statistic. So yeah, Anova is really cool. Serrano Fisher invented it. That's why when we obtain our value for it, it's called an F value. It's for Fisher. All right, time for a story. Okay, let's suppose you have a friend, and let's say he's built a Tesla coil in his front yard, and he says, I need to test my Tesla coil out, see if this thing works. So I'd like you to walk by it. Now, I'm going to pay you every time you do. I'll pay you, say, $5 every time you walk by it. You say, that sounds good, I'll help you out. I like to make some money. He says, oh, but there's this one thing. You could get shocked by this Tesla coil about 5% of the time. Now, how many times would you want to walk by that Tesla coil if 5% of the time you're going to get shocked? Depending on your personality, there's probably a different answer for that, or your need for money. Let's say I raise the stakes a bit, or he raised the stakes, because I don't, you can see in my front yard, I don't have a Tesla coil. I do have an electric car, see? Chevy Bolt, good car. Way cheaper than the Tesla. If I raise the stakes to $500 every time you walked by that Tesla coil, do you think you'd walk by it? How many times? Once? Twice? Twice and you get $1,000. Now things are changing, right? What about $1,000 every time? Some of you are still going, no, I don't want to get shocked. It's not worth it. Not worth the risk. What about 10,000? You might be wondering, what's this analogy about? The analogy here is for research. You see, we've gone over hypothesis testing with t-tests. And the problem is that we can only compare two things in that instance. If I wanted to compare three things in that instance, there becomes a problem. So why can't I just use a t-test for multiple analyses? I mean, you can, but the issue here is, let's say I needed to test a new drug. I have a new drug, and I want to see if it cures cancer. I've got a 5 milligram dose, a 10 milligram dose, and a 15 milligram dose. I don't know which one is going to be the effective level. The problem with cancer drugs is that oftentimes they're pretty terrible for you, and so you want to go with the lowest, what's called effective dosage. You want the minimal amount that's going to be clinically effective at reducing the cancer. And if I do a 5 milligram dose versus the 10 milligram dose t-test, let's say I do a t-test for independent samples, and I have two groups of people, and I have one group that takes 5 milligrams and one group that takes 10 milligrams. What's the probability that if I find that there's a significant difference between the two, that I'm wrong, or that I've made a type 1 error saying there's a difference when there's not? Well, that's easy. Alpha level 0.05 means that there's a 5% chance I'm wrong about that difference, and that the difference that I saw was just due to sampling error. It's just chance. Well, that's a 5% chance that we're willing to go with. But see, I've only determined if there's a difference between 5 and 10 milligrams, not between 10 and 15 milligrams. So let's say I run another analysis between the 10 and the 15 milligram dosage, and I run that 10 milligram group versus a group that say I give 15 milligrams to. And let's say I find there's a statistically significant difference between 10 and 15. Well, then I have to run another one to see if there's a difference between the 5 milligram and the 15 milligram. So now I've done 3 analyses. Each of those 3 analyses has a 5% chance that if I determine there's a statistically significant difference, I'm wrong. So now instead of having the probability of being wrong 5%, I'm up at 15%. So this is the problem with running multiple t-tests. This has been a significant problem for psychology and our replication issue. And so it's something that needs to be addressed. And the brilliant man, Sir Ronald Fisher, who figured this out, really helped us. Now, there was somebody who figured out a solution before this, and I'm guessing you probably could. So how do we set our alpha level? It's whatever we're comfortable with. It's however comfortable we are, whatever comfort level we have with being wrong and making a type 1 error. If it has something to do with what type of educational mode is going to be better at teaching students, or what makes us more attractive to the opposite sex, or something that's sort of trivial, we might go for an alpha level of 0.05, but we choose that alpha level. If it's something like brain surgery, we're going to go with a much more stringent alpha level, like a 0.01 or a 0.001. We are in charge of our alpha level. So what you can do is arbitrarily take however many analyses we're doing, let's say 3 of them, and we'll say we want to only be wrong 5% of the time with these 3 analyses. We can reduce each of the alpha levels so that when they add up, we know we're doing 3 t-tests, they will equal 0.05. Now, this is something that I like to do with class. Oftentimes, I kind of coax you guys into it, and inevitably, there's somebody in the class goes, well, we could just lower our alpha level so that all 3 analyses equals 0.05. And I say to them, congratulations, Dr. So-and-so. And I say that not because I've conferred upon them a doctorate, but as an honorary doctorate. Because I want you to see that your sense of logic and understanding and the amount of stats that you've already learned gets you to a place where you can make a discovery that if you were, 100 years ago, the Bonferroni Correction. I don't know if it was 100 years ago. Somebody look that up right now. But Bonferroni came up with this correction of just arbitrarily lowering the alpha level so that we got the desired aggregate alpha level for as many analyses with t-tests as we were doing. That's not what Anova is about. See, the problem with that is that you're increasing your chance of what's called a type 2 error, and that is that you're going to miss an effect of the independent variable on the dependent variable if one exists by lowering your alpha level, right? There's this trade-off. So Sir Ronald Fisher came up with a brilliant solution. So we'll talk about the solution he had next. About the Tesla coil. Totally forgot about that. So if you could walk by it as many times as you wanted and only have that 5% value of being shocked, you could increase the chance that you find something significant. And now let's relate that to research. If I'm a researcher and I want to do my cancer study with the 5, 10, and 15 milligram dosage, but I only want to be wrong 5% of the time, I can reduce the probability that I'm making a type 1 error to that alpha level and run as many analyses as I want with Fisher's solution, which is the Anova, or the analysis of variance. What the idea here is that you take as many groups as you want, and then you individually look at the variance and their projection of the population that they came from variance, and then you look across them. And this allows us to sort of compare what we would expect given no difference between the groups, our null hypothesis, and it allows us to sort of get the probability that there is a difference within those groups. So that's why researchers love Anova so much, because it enables them to find differences and then get published. Again, a replication problem aside, you're only going to get published if you find a significant result. And if you find a significant result by doing many t-tests, you're increasing your alpha level, and that's kind of cheating. But if we do an Anova, you can find a significant difference between things by just doing one analysis, holding the alpha level steady, so that we're not having a high risk of being shocked. And what I mean by being shocked is if we publish something and we say there's a statistically significant difference and it turns out that that's wrong, then when people find out that my research was flawed by, say, replicating it and being unable to find that same statistically significant difference, I'm going to lose academic credit. I'm going to be the laughing stock of my peers. And people won't trust what I say. So that's why we want to make sure that when we do ANOVAs, we take into account that possibility, but we do as many analyses as we can in order to find differences where they exist in human populations. All right, I hope that helped. You might be asking yourself, why am I showing you this picture of Tupac at Coachella? Well, part of the reason is that Tupac died, so he couldn't have been at Coachella. But what you're seeing is an amazing capability of two different perspectives, or in this case, a lot more than two different perspectives on Tupac when he was alive performing. And it's come together as a hologram. And each of those different perspectives is important because it's showing different angles of Tupac performing at Coachella. I can't press mute on this because you can't, I couldn't do this. Anyway, too much swearing. But right now he's doing Hail Mary, and you can see it looks just like him, right? It's an approximation of him. It's, I don't know, it's a projection of him. And it's multiple projections. You see, if all these projections are the same person at the same time from different angles, you're going to see something that looks like the real thing. So this hologram is the idea that we're going to use to explain Sir Ronald Fisher's take on Anova. And for those of you that don't know, he is one of the greatest two rap, R&B, hip-hop stars of all time, with him and Biggie Smalls. Now, if I took a picture of Biggie Smalls, again, he's dead. But if I took Mr. Wallace and Mr. Shakur and I put two pictures of them together, or I guess I could take Snoop, but he's not a very good comparison to Tupac. Biggie would be a much higher level artist. That's just my opinion, just in my opinion. But if you took a picture of Biggie, who was a very large man, and Tupac, who's a very small man, and you projected two of those pictures onto here, you wouldn't see the same thing. You wouldn't see both the same perspective on Tupac. It would be a warped picture, and it wouldn't look correct. It would look very different than a real person. Whereas this hologram, sorry about Snoop there, but you wouldn't see that perspective on Snoop. You would see only a jumbled mess, and you'd really recognize that there was something different from those two different perspectives. So that's what we're going to talk about with Anova, perspectives and estimations of the real thing. Baby. Okay, we're back here at the whiteboard, and we've been talking about Anova. So Anova is, again, just like I gave you the example of the hologram. If you don't like rap music, perhaps you like Star Wars. If you remember, help me, Obi-Wan, you're my only hope. R2-D2 is projecting out two pictures or two or more perspectives on Princess Leia as a hologram. And that hologram allows the visual imagery to be there so that we can see it's Princess Leia. And the hologram is a neat perspective because it gives you a better sense of the whole than it would in a two-dimensional image. So if R2-D2 got his wires mixed up, circuits mixed up, and he projected a picture of Chewbacca and one of Princess Leia, it would be a jumbled mess and it wouldn't look correct. Same thing, if at Coachella they showed Biggie Smalls in one perspective and Tupac in another, it would be a jumbled mess and you wouldn't see anything. It needs to be both Tupac from this angle and Tupac from this angle, so those two estimations of Tupac present something that looks like the real thing. And that's what Sir Ronald Fisher figured out. Now, Sir Ronald Fisher, turns out, was a jerk. The book has a little blurb in there about him being a mean person to his nanny when he was like 3, like basically calling her a dimwit. But he was really, really brilliant. And he figured out this. He figured out that, look, if I take estimate of population variance, right, an estimate, just like one estimate of Tupac is this angle of light, and another estimate of Tupac is an angle of light like this. He said, if I take two perspectives and I compare them to one another, I put them in ratio form, I'm going to be able to see if it's talking about the same population, or if it's Tupac and Biggie, or if it's Chewbacca and Princess Leia, right? Something different. If I put them up next to one another, remember this hologram imagery, and it shows me the same thing, I'll know there's no difference across these groups. So the ratio form that he figured out, so the F is equal to mean squares between divided by mean squares within. What we're going to see here is the difference between the groups showing us that same perspective as we see the difference within each of these groups, right? If I have my example that I gave you before, which was there's a 5 milligram, a 10 milligram, and a 15 milligram dosage of this anti-cancer drug, then we'll see, is the difference between each of these groups, the mean squares between, the estimate of population variance from the differences between their means, telling us the same thing as the estimate of population variance that I do within each of those 5 milligram, 10 milligram, and 15 milligram groups and average them. Because again, if the null hypothesis is true, all of them come from individually the same population, so I could aggregate them together and make a better estimate of population variance. So that's the basic logic behind Anova. Again, if you're struggling with this right now, please relax. Take a deep breath. Anova is the analysis of variance. We know how to calculate variance. We know how to estimate population variance. That's that S2. And we're just going to do it two different ways here and see if they tell us the same story. If they do, there's no difference across these groups, right? My 5 milligram, 10 milligram, 15 milligram group. But if the difference between the means of those groups, let's say the 15 milligram group, the cancer cells are like not even there, but the 10 and the 5 milligram groups, they see cancer cells still there, then the difference between the means of these groups is going to be big. But if the difference in the variability within each of those groups is small, then I'm going to have a large F ratio. We're going to see a way that we can estimate this and play around with it to sort of see the difference between groups big and the difference within groups small would provide a large F value. Whereas if there was a lot of variability within the groups and only a little bit between, we would just say, hey, this is showing us Princess Leia and Princess Leia, or Tupac and Tupac. It's the same thing. There's no difference between these groups. Okay, a couple things about Anova that I want you to remember. One is that while it's the most commonly used inferential statistic, it's the hardest one we're going to see. And there are some terms that you should understand. Obviously, we've already covered that Anova is short for analysis of variance, but there's something else. In Anova, we don't call the independent variables independent variables. We call them factors. And that's fine. I mean, you can make the difference there. Another thing, on the PowerPoints, you might see mean squares between. It might be labeled S subscript B squared. If you think about it, it makes sense because this is just the variance estimate from between groups. That's the means between groups, how much variability there is between the groups' means, and then using that to estimate the population variance from which those groups are drawn. Assuming the null hypothesis, of course, that they all come from the same place. Now, each condition of the independent variable we call a level or a treatment. So the differences that are produced by the levels of these factors are called treatment effects. Also, the symbol for the number of levels, how many, in my example of the 5, 10, and 15 milligrams for the anti-cancer drug, that would be 3 levels. So instead of saying like number of levels is 3, you say K is equal to 3. So K is the symbol that we use to talk about levels of the factor. Only two-tailed comparisons are made in an Anova, so you don't ever make a one-way. A one-way Anova is never a one-tail test. It's always a two-tail test from that hypothesis testing standpoint. So let's talk about the null hypothesis. All right. For an Anova, you might think that the null hypothesis is that the HO would be that the mu for group 1, that is equal to the mu for group 2, is equal to the mu for group 3, is equal to the mu for group, and I'll put it there, K. That just means however many more levels there are. If I had a 5, 10, 15, 20, 25, 30, 35 milligram protocol where I was analyzing them, it would just be however many means there are for those samples that I had. So this is the null hypothesis that basically says, look, all of them are the same. In an original, like in a t-test, it would just be mu1 is equal to mu2, right? We only had 2 comparisons. Now we're including however many levels of the factor there are. What might you say is the HA? Is it mu1 does not equal mu2? Does not equal mu3? Does not equal mu-k? No. In fact, the alternative hypothesis is that just one of these levels did not equal the other. So insert here the little Sesame Street. Which one of these is not like the other? Which one of these does not belong? So the alternative hypothesis of an Anova is that at least one of the levels is statistically significantly different from the others. Okay, so not all mu's are equal. That's what we're saying. Basically what we're saying is that the probability is that this mu represents that it's drawn from a separate group. It's unlikely to have been drawn from this group. Okay, so we're going to now go through an example problem of how to calculate an Anova, an F value, compare it to an F critical value, and do those 6 steps of hypothesis testing. Several examples in the book. One of them is about attachment style. One of them is about criminal background. So let's do the one about the criminal background and analyze the variance that way. Okay. We're back. Do you know who the most famous psychologist is? Some of you might say Sigmund Freud. Some of you might say Carl Rogers or Carl Jung. Nope. Good old Phil Mcgraw, Dr. Phil, is the most famous psychologist. And the reason he's the most famous psychologist is that he got hooked up with Oprah and he helped her. So if you're not familiar with this story, Phil Mcgraw was a consultant for a forensic psychology firm, and they helped Oprah prepare for her trial and did jury selection work for the lawyers who were defending Oprah when these Texas beef cattle ranchers sued her. They said her statements that she would never... Remember that pink sludge stuff was coming out a while back, and they were showing all the processing of meat and like how you get your hamburgers for like fast food patties and whatnot. They were showing all this stuff, and so Oprah said on her show, I'll never eat a burger again, or something like that. Well, they sued her for millions of dollars in libel, I believe, and sort of saying that what they were selling was bad. So Phil Mcgraw was hired by her lawyers to help prepare her for trial and then also to help do jury selection. So he is fabulously wealthy. And that being said, if you want to get really rich using psychology, learn to use statistics to help lawyers in medical legal cases. You might have to sell your soul to the devil, but that's again, you're trying to make money, so there you go. I'm not claiming Dr. Phil sold his soul to the devil, just so I don't get sued for libel. But industrial organizational psychology and forensic psychology used in litigation is really sort of the way to make money in this business. Only, however, if you're using statistics. And I'm sure that the example problem we're going to use here is a similar setup to what would be done in most situations in trying to figure out how does a psychologist help an attorney during pre-trial preparations. All right. In our case, the book uses the example of how do jurors rate the defendant's guilt after watching a trial, and say they use a scale of 1 being, pure as the driven snow, to 10 being totally guilty, needs to go to jail. And this is about a criminal drunk driving case. So that's what the book uses. Just a PSA right now. Every 48 seconds, a drunk driver in the United States makes someone capable of parking in the handicap spot. So, don't drink and drive. Good news, your generation's not drinking and driving as much as my bad generation, but you're doing something worse. You're driving and texting. Now, why is that worse? Well, it turns out that if your eyes are off the road, rather than being slow reactions from drinking, don't drink and drive. I'm not telling you to drink and drive, but that's actually worse and causes crashes more often. And so be careful about that. This is an example of criminal drunk driving case. And so we're going to take the numbers here and let's make 3 groups of 5 people. So we've got these prospective jurors. These prospective jurors are given 3 different kinds of information. One group's given no pre-trial information, like they don't hear anything before the trial about the defendant's driving record. So nothing's given to them. They kind of act as a control, if you will. That's like if I had, remember my groups of 5, 10, and 20, 5, 10, and 15 milligram. If you had a 0, 5, and 10 milligram, that 0 would kind of be the control because you didn't actually give the drug to them. So in this case, the one group is given no information about it. Then there's 2 different groups. One group's given information that suggests that that person has a criminal background of drunk driving. So this is drunk driving background. So there's 5 of them. And those 5 people rate the defendant's guilt. They say, okay, on a scale of 1 to 10, 1 being totally innocent, 10 being guilty, needs to go to jail. How do you rate this person? And so the ratings are as follows: 10, 7, 5, 10, 8. Now, if you add those up and you divide by 5, you're going to get 8. The mean is 8. So the mean rating for this group was 8. That is that they thought that the person was pretty darn guilty after they watched the trial, right? They were given information saying this person had been convicted of drunk driving prior to this trial in a different case. Do you think that your perception of someone's guilt would be influenced if you heard stuff before about a different case? This is oftentimes when, in criminal cases, people want to suppress former convictions. So the defendant's attorneys are going to want to suppress if this person's been convicted before, because they think this is going to influence the perception of the juror's guilt, how much the jurors perceive the defendant to be guilty. But we don't know that. We're going to compare that to, what if we gave this person a clean record, a clean DMV record? So we told the people, this person, again, we selected 5 people. Now, all of these groups are going to have 5 people. They don't necessarily have to. They could have multiple differences between these groups. But I'm going to do it like the book does it, because for calculation purposes, we don't have to take into account, remember S2 pooled from the last one where we had to aggregate them and then weight their sort of within group variance? That's the numerator. That's the denominator in this F ratio. In t-tests for independent samples, we took both groups, regardless of their size, but then we made their influence on the projection of population variance weighted based on the size of their n, or how large the sample size compared to one another. We could do that, it just gets very complicated for hand calculation. So we're going to make them all even, and then they all have the same influence on projected within group variance. Okay, so here are the ratings for this group of people. Before they watched the trial, they heard that this person has a clean, no parking tickets, no speeding tickets, nothing, clean DMV record. So here's their perception of guilt: 5, 1, 3, 7, and 4. If you add those up and you divide by 5, you see that the average, or the mean, for group 2 is 4. And finally, we had our control group. None of them got any information about, so no info. The no info group, again, there's 5 of them. Their ratings were 4, 6, 9, 3, and 3. Now that adds up to 25, and 25 divided by 5, well, mean for group 3 is 5. So see, we have these 3 different means. The question is, are those means different enough to suggest that the different information that they're given pre-trial to watching this trial influences the juror's perception of guilt? Now, what do I do with those means? I'm going to take each of those means and I'm going to consider how to create squared deviations from the mean, or SS for group 1, SS for group 2, SS for group 3. So if I do that, you know how you subtract from each of these the mean? So subtract from 10, 8, you'll get 2, which is a deviation score. You square it, you get 4. Okay? If I do that for all of these, the sum of squares for group 1 is 18. Now that I have sum of squares for group 1, that's 18. You can't see this at all. Whoops. There we go. Now that I have sum of squares for group 1, which is 18, I can take 18 and I can divide it by the degrees of freedom for group 1, which there were 5 in group 1. So if I divide it by the degrees of freedom for group 1, if you remember this equation, this is what gives us S2. So we divide that by 4 and we get 4.5. Now that is S2 for group 1. So we're going to do that for this one, we're going to do that for this one, and we're going to find out what it is. So if I do that, the S2 for group 2, we found out S2 for group 1 is 4.5. S2 for group 2 will be 5. You can do this hand calculation if you guys want to follow along. Just subtract the mean from each of these individual raw scores. That's a deviation score. Square it to get rid of the negatives, because if you added that up, it would be 0. The sum of deviations will always, from the mean, will always equal 0. So we square it. We get the squared deviation scores. We add them up. The sum of squares, that's the sum of squares. We divide it by the degrees of freedom. That gives us S2 for that group. Same thing we can do for group S2 for group 3. That is equal to 6.5. So we have 3 different estimates of population variance. So we're estimating the population variance from the variance within each group. What do we do with that? How do we get within group variance? Well, in this case, because there's 5 in each group, we're just going to add them up and divide by how many there are. To get S2 within, we're going to add 4.5 plus 5 plus 6.5, and we're going to divide by 3. Okay? When you do that, you get 9.5. 9.5 plus 6.5. Anybody out there? Divided by 3. There's 3 groups. All right, that's 5.33. All right, so we found our denominator for, oh, you still can't see that. There you go. Move you back a little bit. Okay, so 5.33 is our S2 within. It's our mean squares within. And that is going to be our denominator in the F ratio. That's the way that you're familiar with calculating variance, is that we take the group's variance within each group, and then we see what was their projection for that population variance. And now we average across the groups to find the sort of, if the null hypothesis is true, that's what within group variance is telling us. It's saying it comes from a population that has a variance of 5.33. All three of these do. Again, that's one perspective on Tupac, if you remember the analogy of the hologram. This is one perspective on Tupac. If our other perspective on Tupac is like 7 or 6 or 4, something really close to here, that's two projections on Tupac, and you see the hologram, and there's no difference between these groups. But if we see the projection come out not like 5.3, let's say it comes out as like 10 or 28, that's like Biggie or Chewbacca instead of Tupac or Princess Leia. So it's going to show a difference between the two estimations of population variance. We're back. We figured out that the within group variance, or the denominator in the F ratio, is 5.33. That's that we took all the variability within each group and kind of aggregated them to find out what's the average that they said projecting the population variance to be. Fisher said that if we do that, and then what we do is we look at each group's mean and treat that like it's another sample, then we can ask it how much variability is it between the means of the groups. Now we're taking the mean of the group and creating it as a different possible link to the population that it came from. Again, the logic would be that if all three of these groups come from the same population, the means of each of those groups are going to give us insight into how much variability there is in that population. So our drunk driving group, if you remember, they had a mean of 8. The group that had no information, no info, they had a mean of 4. And then the group that got the clean they had 5. They had a mean of 5. And the clean record group had a mean of 4. So these are the three different means that we have. If we add them up, anybody? 8 plus 5, 13, 13 plus 4, 17, good. 17 divided by 3. All right, so 17 divided by 3. The grand mean, I say GM because I'm taking a mean of a means. So the grand mean is you take the means of each of the groups that you're considering and you average it. 17 divided by 3, that's 5.6 extending for forever. Okay, this is our grand mean. I'm going to now take that and subtract it. We'll just use 2 decimals, 5.66. I'm going to subtract from that this will give me deviation scores. So deviation scores are going to be, for us, it'll be 2.33. For 5, it's going to be negative 0.66. And then for 4, it'll be negative 1.66. See how we did it there? Now if you add those up, what do you get when you add up the deviations from the mean? You should always get 0. If you add those up, you're not going to quite get 0. And this brings me to another point. You see how I've rounded each of these? In rounding them, I've lost some information. But the check would still be true that if I add these up, it's going to be a number very close to 0. Because the only problem is that this number isn't actually negative 1.66. It's negative 1.666 extending for forever. So in that case, this is not 2.33. It's 2.333333 all the way off the board, extending for forever. You're going to have some residual. Whenever you round, you're going to miss some information. So if you freak out and you're like, I added these numbers up, Professor Frazee, and it wasn't 0, so I've done something wrong back here. If it's really close to 0, you're still on track. It's just the rounding errors that make us have some residual there. Okay, so because we have that, we're going to now square them, right? If I square them, deviation scores squared, this is going to help us add up to get what we need. So for 2.33 times 2.33, that's 5.43. for 5, 0.66 times 0.66, that equals 0.45 basically. And for 1.67 or 1.66 times 1.66, that's 2.79. Now I add those up. When I get the sum of squares for the grand mean, GM, the sum of squares for the grand mean is 8.67 basically. So now that I have the grand mean's sum of squares, I can then divide the grand mean by the degrees of freedom, 2, and that will give me S2 for groups of 5, S2 sub m. So S2 again is a estimate of variation for groups of 5, not for 3 groups of 5. I'm sorry, for 3 groups, not for 3 groups of 5. We have to modify this in a second. This becomes the complicated version of it. But if I take 8.67 and I divide it by the degrees of freedom, it gives me an estimate for variance from 3 groups. And that's 4.34. So now we have this number. This is not an estimate of the population variance based on 3 groups of 5. It's just the population variance based on 3 groups. What we need to do now is something to consider that these 3 groups, we're using their means. We're not using individual scores, and you can't compare individual scores to means. So we now have to say how many individuals made up each of these groups. And so we're going to multiply this number, S2 sub m, by the number in each of our groups. Each of these groups' mean was created by 5 people. So we're going to multiply S2 sub m times n. And n in this case is the number in each group. So the average in each group. For us, that was 5. So n is the number of scores in each sample. And so when we do 4.34 times 5, that gives us 21.70. That is our mean squares between. Our mean squares between is 21.7. You don't need a 0 there. 21.7. Okay, so 21.7 is the estimate of population variability given the size of these groups and the difference between their means. Remember, that perspective is saying biggie. Whereas the within group estimate, the denominator, is saying 2POC. So what's going to happen now? We're going to put these back together in the ratio form for F value. I guess we'll skip this. I'll erase for you. We have the F statistic, or our F obtained value, is equal to mean squares between, which we calculated to be 21.7, divided by mean squares within, which we calculated to be 5.3. Now, because it's that, we have to think about, well, what does this ratio mean with regard to how often do you see a difference in the estimated population variance between mean squares between being 21 and 5 and mean squares within being 5.3. How often does that occur? That's going to give us the probability. And then if it's a low probability that this occurs, we're going to reject the null hypothesis. So our F ratio is 4.07. Now what we're going to need to do is go to the back of the book and figure out, well, if that's what we're saying here is this is how often this happens, we go to the back of the book and we find our F critical value. The F critical value in the back of the book is a little bit difficult. So let's talk about how we use the F table. The F table is going to ask you to calculate 2 different degrees of freedom. One's going to be the degrees of freedom in the numerator, and one's going to be the degrees of freedom in the denominator. See if you can see that there. Now, if you look across the top, this is the numerator degrees of freedom. So our numerator had how many groups? 3 groups, right? There was 8, 5, and 4. So 3 groups minus 1 is 2. So we go to 2. And then our denominator, this is the tricky one. How many S2s did we calculate when we made that up? Well, we calculated an S2 for group 1, which was we divided sum of squares for group 1 by the degrees of freedom. So there's 1 degree of freedom. There's 1 taken away. For S2, we did the same. For S3, we did the same. So there's 3 taken away from the 15 that made that up. So 15 minus 3 is 12. So we go down here to where it says 12 for the degrees of freedom in the denominator, and 2 where it says the degrees of freedom in the numerator. And let's use a 0.05 value because we can. The F critical value for this is 3.89. All right, F critical value is 3.89. So F obtained is 4.07. F crit is 3.89. What this means is that if we look at an F distribution, it kind of looks like this. It's a skewed distribution. This type of a skewed distribution is actually one that we call a positively skewed distribution. But here's 0. Most likely you're going to get 1. Remember, 1 in this situation means that the numerator and the denominator are the same. And that's saying in the null hypothesis population, if we compare the means of 3 groups that all come from the same place to the within group variance for each group, or each of those 3 groups, we're going to find 1 most of the time. And this is saying, this critical value is saying you got to get out to almost 4, right? 3.89 for us to be at that 0.05 level. That happens less than 5% of the time by chance. So less than 5% of the time by chance means that our score happens less often than there, and it's in the area for the critical rejection of the null hypothesis. So when we get to step 5, we'll reject. Okay, now let's go through the 6 steps of hypothesis testing using what we found here. Step 1. There are 2 populations. In our case, there are 3. Pop 1, let's say clean. Pop 2, let's say no info. And pop 3, we're going to say the drunk driving record. Okay, HO. All the same. They come from the same population. HA, not all the same. One of these 3, at least one of these 3, is not like the other. Oh man, somebody's waiting for food. Feral cat? All right, kitty, you ready to show him your trick? Here we go. See if you'll perform for the class. Come on up here. Come on. Can you see him? Sit up. Come on. Sit up. All right. Trained feral cat. All right, we're back to the 6 steps of hypothesis testing. First thing we're going to do in the step 2 is to determine the characteristics of our comparison distribution. So we're going to think about what would we compare it to. We'd compare it to a distribution that had the same mean squares between to mean squares within. So the mu difference would be 0. Now the standard deviation, right? So the sigma that we'll accept for the difference between these means is going to be our alpha level considering these 3 groups. So we're going to leave it like that for now. Step 3 is to find out where determine our sample's cutoff score on that comparison distribution, and we did that. That was 3.89. And then step 4 was to put our sample score, so the F obtained of 4.07, put that here. Step 5, reject HO. Now, I've gone through these really quickly because I want to get to step 6. What do we say in step 6? So the lawyer comes to you and says, hey, you ran these groups. I paid you all this money. You forensic psychologist, you statistician, you genius. What do I do? You say, there's a difference. We've rejected the null hypothesis. There's a difference in those groups. So then the lawyer says, okay, what do I do with that information? How do I actualize that to benefit my client's goals? Now you're going, well, I know that at least one of these 3 groups is not like the other. And the lawyer goes, which one's different? Or are they all different? Which one's different? What's the effect size? How much? So we have more to do here. We got to figure out where the difference exists. Now that we know there's a difference, we go looking for it. Now you might be saying to yourself, this seems stupid because we just did all that whole thing and we found out there's a difference, but we don't even know where it is. It's not stupid. I'm giving a simple example. The book gives simple examples, and this applies to grander scales, which allows us to do really interesting research. So Anovas are tremendously useful, but they're limited. They tell us that there's a difference in the groups, but they don't tell us where that difference is. For that, we're going to need to go to what's called post hoc analysis. For those of you that speak Latin, post hoc means after it happened or after the fact. We've run an Anova. We did it. We figured out, we reject the null, not all these groups are the same. Now we need to go back and say, well, where are the differences? Are there differences between no information and the clean driving record group? Is there a difference between drunk driving and the clean record? Or is there a difference between drunk driving and the no information group? We need to figure that out to help the lawyer or the attorney for the defendant actualize this information to benefit their client, to make us worth our money being paid, not to seek justice, to benefit our client. So now let's go and find out about post hoc analysis.